like to start by pointing out that you can have three main takeaways from this slide. So the first one is that we are willing to be in San Francisco all together. So that's the background that you see on the slide. The second one is the URL link at the bottom, which is the link of the workshop website, where you can find all the program and details about the presenters and talks that we're gonna listen today. And the third point is our sponsor, bottom right there, you see Avast. We are very thankful to the sponsor for supporting us in putting the workshop together. So the workshop chairs, you can see them here, is Nicolas Vasiloglu, and myself, Battista Biggio. I'm an assistant professor at the University of Cagliari, and Nicolas Carlini as well. We are the three workshop chairs. And of course, I mean, we are thankful also to the program committee and all the steering committee and publicity chairs that also helped us shaping all this program together for today. This is, as I said, the third edition of this workshop. These are the three links for the other, for the other two workshop editions, 2019 and 18. And this year as well, we are going to post videos of talks after the workshop on YouTube. So just a quick reminder to the authors, just to be sure that they fill in the consent forms that I sent them via EasyChair yesterday, so that we can post the videos after the workshop on a YouTube channel. These are some basic statistics from the workshop. So we had 33 submitted papers. We were able to provide 4 detailed reviews for each paper. And we discussed, there was a subsequent discussion among the reviewers, especially on borderline papers, to make a final decision. Eventually, we decided to accept 11 out of 33 papers. So the acceptance rate is 33%. And just to mention that we had many submissions from different countries, and the ones that you see listed here, Canada, China, Germany, and US, are basically those that have been selected, whose authors have been selected today for presenting. That's a rough course schedule of the workshop for today. So right after the opening, we will have a keynote session, and there will be another keynote in the afternoon session. Then we will have 4 sessions with different number of papers each. Deep learning for security, security of deep learning against poisoning attacks, another session on deep reinforcement learning, and the last session on the, again, security of deep learning and in industry perspectives. We will see these in more detail as we go through, but just to mention the 2 keynotes that we are going to attend today. So the first one will be given by Wieland. So hi Wieland, I see you there. And it's about defending against adversarial examples. And I will give you some more details about this later. And so this keynote will be right after this opening. And then in the afternoon, you'll have the other keynote speaker, Professor Ani Farid from UC Berkeley, talking about the detection of deepfake videos. Another quick thing to note is that the proceedings are already available. I think there is a mistake in the slide. They should be IEEE proceedings. But you can find the link on the website, and they are accessible with user and password that you should already have gotten from the subscription web server. So some basic rules for interaction with speakers. So every talk will be roughly 20 minutes, of course, except the invited talk, the talks which will last longer. But after the talk, there will be 5 minutes for a Q&A session. The way we'll handle this is that the attendees can write their questions into the chats, and then the authors will answer some of them right after the talk in this 5-minute session. For other questions or try to reach out with the author, we will use Slack. You should all also be connected via Slack. So we have this channel DLS for the workshop, and then we also have other channels. So one channel for each paper and presenter, which you can identify by the simple syntax that you see here. So you have DLS underscore the first name.
Just a correction.
Yeah.
But this is actually DLS dash. It's not underscore.
Yeah, okay. DLS dash, and then you have first author's last name, right? So you can find here in these channels the presenter, and you can contact them out after the talk, okay, during the break sessions, which are already listed in the program. Another thing you may be interested in this Avast Zoom room. So the sponsor is some of the employees from Avast will be available in this room if anybody wants to reach them and talk about opportunities at Avast, or if you have any special issue to discuss with them, that's the place to go. I will just copy this link into the DLS channel so that it's readily available for people who are interested in contacting them. There is some other related announcements here. So one is this workshop and conference, Cybersecurity and AI, which is organized by Avast. It's a nice event. I attended last year, and there were a lot of interesting talks. There is this submission, because they are welcoming submission this year as well. And some of the speakers are listed there. This will be on the October 8th this year. So that's one related event which we are happy to describe here. There's another related one, which is basically another related workshop, which is AISec. This is co-located with the CCS, and this year it will be on November 13 in Orlando. So if you want to have more details about this, feel free to connect to the aisec.cc website that you see there. So let's now it's time to introduce the first keynote speaker. Professor Wieland Brendel is working at the Tübingen AI Center now, and he's going to talk about defending against adversarial examples. And to do that, we need to understand human vision. So that's the topic of the talk. Just to mention some aspects from the biography of Wieland. He is now principal investigator at the Tübingen AI Center. He has been covering this position since 2018, after 4 years of postdoc, being a postdoctoral researcher at the University of Tübingen. He got a PhD in computational neuroscience from the École Normale Supérieure in Paris. And this was after a master degree in physics in 2009. Wieland has done impressive work on robustness and interpretability of machine vision models. He has published on ICLR, NeurIPS, and other machine learning conferences. And he is one of the authors of the widely used Python library Fullbox, which is a Python library that you can use to generate adversarial examples against deep neural networks. So having said that, I think we can welcome Wieland with a big virtual applause, and then I think we can stream the talk, and because that's the plan. So we have a pre-recorded video of the talk that I think Nicolas can start sharing, and then you can write questions, and Wieland is here to answer questions after the talk. I don't know if Wieland, do you want to say anything just before starting?
Just well, first of all, hello, and thanks for the very warm introduction. So
yeah. You're welcome. You're welcome. So let's hear the talk, and then we will connect back. Thank you.
So let me know if you can.
So first of all, thanks to the organizers.
You can hear it.
And of course, also thanks for inviting me to give this talk. Now, you should know that my personal background, at least during my PhD, was in computational neuroscience. And so much of my work in the past few years in representation learning has been inspired from a perspective on human vision. And the same is true for my work on adversarial examples. Now, I see adversarial examples really as just one failure case out of a whole range of failure cases, which are all intimately connected. And I think this perspective of this wider class of problems that hamper machine learning and machine vision in particular is very useful when we're talking about solving adversarial robustness. And that's what I want to talk about today. So all of you will be intimately aware of minimum norm adversarial examples. So you take an image which is, let's say, correctly classified as a frog, and you search for the smallest perturbation, which, let's say, changes the decision of the model to crocodile. And in an ideal world where our models behave pretty much like human vision, you would expect that the smallest perturbation is actually semantically meaningful. So say you get this crocodile hat on the frog body. But of course, unfortunately, we are not living in an ideal world. And so the actual smallest perturbation that suffers to change network decision are almost imperceptible to humans and doesn't change anything semantically. And that's a big reason why we're interested in studying adversarials. But there are kind of three directions or motivations for why we study adversarials. A big part of the community is coming from a security background. So from this background, it's clear that these almost imperceptible adversarials can pose a security risk in many applications, let's say in autonomous driving, or also not safe for work filters and other areas. And so that's a strong motivation to trying to prevent adversarial examples. Another part of the community is coming from the perspective of robustness. So there it's much less about an adversary, but about trying to understand how robust the system will be if deployed in the real world, where things are usually not the same as in my IID training data. And so there we ask the question, okay, what is kind of in what range can I expect the model to behave reasonably well? And so in this case, if you look at the worst case bounds, then you end up looking at adversarial examples again. And the third part of the community is more coming from the comparison between human and machine vision. So basically, as adversarial examples as kind of a benchmark for measuring our progress towards human level abilities. And that's kind of the area that I want to focus today. So why is there even a question of comparing humans and machines? Well, from a very high level perspective, you have like the human vision system and machine vision systems today kind of share at least some rough structural similarities in the sense that both are composed of a very large number of neurons, which are connected by an even larger number of synapses or connections. And of course, we have functional similarities. So we have a range of complex cognitive tasks that can now be solved on superhuman level by machines. And so taking together the structural and functional similarity, at least from a psychophysics perspective, makes you ask, okay, how close is the information processing between humans and machines? How far apart are they still? And in that sense, adversarial examples are kind of the clearest gap between humans and machines, right? Showing that machines are using some features in the image for which humans are pretty much insensitive to. So it's one of the clearest and strongest gaps between human and machine vision. But it's far from the only gap, right? So if you look at more systematically on in which directions basically human and machine vision is different, then you end up with a whole range of different failure cases. One, of course, is domain shift, right? We know that if you show a child, let's say, some textbook comic examples of a penguin, and then you go into a zoo and you show the child a real penguin, it will immediately recognize the correct animal name. And that is something that, at least right now, our machine vision systems are usually not capable of, and domain shifts usually trip them. But there are other traps as well. So just applying some distortions, be it, let's say, compression artifacts, some Gaussian noise on top, which definitely don't change the semantic meaning of the image to humans, they can still change the decision of neural networks. Same if you show, an unusual pose to a neural network, or if you texturize an image, this will change the decision of a machine vision system, but usually not of humans. Or if you change the background to something unusual, let's say a cow on the beach, this can also change the decision of the model, while still clearly showing the same animal or main object to humans. And there's also the other way around. There are some generalization directions that are clear to machines, so for which machines have the same decision, but which clearly change the semantic meaning to humans. So basically, there are a whole range of failure cases, and I don't think that they're separate and isolated from each other, but rather what we argue in a recent perspective, and which kind of reviews a lot of work and thoughts from the community from the past few years, is that all of these failure cases are actually connected from what we call shortcut learning. So what I mean with shortcut learning is the following. Imagine you have this very simple toy data set. It's a data set which is composed of stars and of moons, right? And I show you the labels that I want to give to each example. And now if you test on an IID test set, which is drawn from the same distribution as the training set, then humans and neural networks will categorize the data or the test set in the same way. And typically humans, just use, they react to the shape, right? We have the stars and the moons, and that's the label. And it looks like the neural network is kind of doing the same. However, if you try an out-of-distribution test, so if you change a few factors in the generation process of the data, and in this case we're changing the location of the moons and the stars a bit more, then you end up with very different decisions. So for humans, if you in this out-of-distribution test set, we would still typically classify the images according to the shape. However, the neural network shows a different decision, which, at first sight doesn't really make a lot of sense. But if you look more closely, then you will realize that in the training set, there was a correlation between the label and the position of the object. So the stars have always been in the training set on the top right or bottom left, while the moons have been on the top left or bottom right. And actually, that's the feature that was picked up by the neural network. Now, you won't notice this as long as you stay in the same data distribution. But as soon as you go to out-of-distribution tests, things might be different. And so the usage of different features here explains why in this particular OOD test, humans and machines behave differently. And we would call here of course, when you design such a data set, you usually, as a human, have something in mind, some feature that you think needs to be used in order to classify an object. And in our case, this would be kind of shape. So these failure cases in OOD directions are actually kind of surprising to humans, because we didn't really notice that there was this other statistically relevant feature available for classification. And this is what I call a shortcut. A shortcut is basically a feature that helps you solve a task, but which was not really intended to be used by the designer of the task, so to speak. And that's something that comes up in basically all areas of machine learning over and over again. And to give you one concrete example on IMAGENET, there we have a shortcut which is a texture bias. So I want to show you, so let's jump right into the details. So what we did was to create so-called Q-conflict images. So we took an image of a cat and we combined it with the texture of an elephant using neural network-based style transfer. So if you look at this image, the shape is from a cat and the texture is from an elephant. And we showed these Q-conflict images to both humans and machine vision systems and asked, okay, what do you see? What is the main object that you see in the image? And across 16 categories that we tested, humans predominantly respond with the shape category. But if you ask a machine, they will predominantly respond with the texture category. So this is true for Resident 50, but it's also true for a lot of other vision systems. Let's say AlexNet, DenseNet, VGG, and so on. All right, but why do neural networks neglect shape? You know, we kind of expected when we trained a neural network on ImageNet that they kind of use similar features as us to classify the image, but now we realize that this doesn't seem to be the case. Well, the reason why neural networks neglect shape is very simple, because they can. They don't have to use shape. There are sufficiently many other factors and features around, like texture, which are already sufficient to solve the task. And to make this even more concrete, consider the following example. So here what we did was we took an image and we basically split it up into individual patches. And then we fed each patch in isolation to a neural network. And so the neural network had to extract class-level evidence on each patch for each class, let's say for lizard and for tree. And it had to do that for every single patch in complete isolation. And then we just summed up the evidence across all patches, computed the probabilities, and this is basically our image-level decision. Now, if you do that, this network here is basically not capable to do any kind of nonlinear integration of features which are larger than the patch size. And so if the patch size is small enough, you're guaranteed that nothing like shape can actually be used by the model. And this is actually very instructive. So if you use very small patches, let's say 9 by 9 pixels, then you will have a top 5 validation performance of around 70%. Now, in these 9 by 9 patches, it's really, you only see basically a few color blobs, maybe a bit of gradient. So there's very, very little information available, at least to the human eye. If you increase the size to 17 by 17, where you start to see at least some small parts or features, you can basically reach AlexNet performance. And if you increase the size even further to 33 by 33, where you definitely start to see some subparts of the objects, but really not the shape itself, then you reach around 87–88% performance, although I'm pretty sure, with further tuning, you can get quite a bit higher. So that's pretty interesting. So this kind of bag of parts approach, which is really the simplest thing that you can think about, right? It's really just summing up local evidence across all the image. That's basically what people have been doing in the pre-deep learning era. That's basically already sufficient to solve ImageNet. And it's pretty interesting what that reveals about the decision-making process itself. So these, we call them BAGNETS. If you ask, okay, what are the important patches that for which you predict a tench, so tench is a big fish, then you actually end up with images where the fingers in front of a greenish background seem to be highly predictive for a tench. Well, why is that? Well, the reason is pretty simple, because basically almost all tench images are trophy images where the fisherman is holding up the tench. And so that makes this particular feature a very predictive one for this class, and it also explains some of the failure cases where we see some hands in front of a greenish, grayish background, but which are actually not from a tench. All right, so in essence, we now understand that ImageNet can be solved really without taking into account any larger spatial relationships, and definitely not shape. It's not needed. And so neural networks, at least in principle, could completely neglect object composition and just classify the images in terms of a bag of parts approach, just like in the pre-deep learning era. And that's actually, so in this work, I'm going more into detail, But that's actually what we found. So we performed a whole range of comparison experiments between neural networks and like standard neural networks like ResNet 50 and the BAGNETs. And from all experiments, one can see that the basic mechanisms, classification mechanisms of typical networks like ResNet 50 seem to be very similar to BAGNETs. All right. Now you could argue that this is not a bad thing, right? It's like, I mean, it's a valid approach to classify images, and that's absolutely true. But of course, there's a reason why humans developed a shape bias. And the problem here is that if networks use this bag of parts approach, then of course you run into issues, right? So if you, for example, take one of the parts, let's say the necklace, which is weakly correlated with the object category, and you basically just throw out everything else and you just replicate the necklace, and each necklace just provides a little bit of evidence to the overall decision for, let's say, a face, then the rightmost image here for a bag of parts model would provide a lot of evidence for the face category, while humans would clearly not classify this as a face. Okay, so by using this approach different from humans, or this classification approach which is different from humans, you start to have generalization directions in which the decisions of humans and machines start to differ. And of course it also explains, for example, why this bag of parts model also explains why neural networks are so susceptible if you change the background. What it did was to learn that, of course, grass is always weakly correlated with the cow class, whereas, let's say, water is weakly anti-correlated to cows because it usually never sees cows in water. And so if it sums up the evidence across all patches, then you naturally end up with these kinds of decision problems where flipping out the background for something unusual changes the decision of the machine vision model, while humans recognizing shape here, of course, still recognize this as a cow because they basically mostly ignore the background. All right, now the question is, can we, now knowing this difference, knowing that machines seem to mostly ignore shape while humans don't, now the question is, can we kind of make neural networks develop a larger shape bias? And one of the ways that you can do this is to basically take ImageNet and to replace the natural texture of the image by an artistic texture drawn just randomly from artistic images. And doing that, you basically throw out all texture information. And so, the hope is that networks have to learn much more about shape in order to correctly classify images. And that's indeed what is happening. So a shape, called shape ResNet, which is trained on these stylized images, develops a much stronger shape bias in some categories, almost approaching human level shape bias. And that actually brings a range of advantages. So first of all, you get slightly increased ImageNet performance. We see if you use this shape ResNet as a backbone on Pascal VOC, we see around a 5-point increase in performance, and we also see an increased performance or increased robustness against natural corruption. So here in ImageNet C, it's shot noise, focus blur, and so on. And this model was actually state-of-the-art for some time on this benchmark. So actually, shape bias does have an advantage. It's just not very relevant if the sole objective is maximizing classification performance. Okay, so that's kind of clear now for texture and shape, right? So it's clear that texture, you can call it a shortcut, in a sense, can be used to solve ImageNet without ever really looking at shape. Question is, are adversarial perturbations kind of in the same range? Should they also be seen as features which are, used by networks for classification, or is that kind of some other kind of bug which is dissimilar from this texture versus shape discussion? Well, the answer to that comes from Alexander Mahdi's lab in the seminal work from 2019, where they looked at whether adversarial perturbations are bugs or whether they can be seen as features. And without going into details now, what they found is that indeed adversarial perturbations are not just random things happening, but they actually seem to pick up features which are relevant for classification. It's just that we as humans are basically not sensitive to these directions. Okay, so meaning that adversarial perturbations are really basically patterns in the data, but we as humans are just insensitive to that, so we don't recognize them. And that kind of, already ties together these two very different modes, adversarial examples and this texture versus shape discussion, as again under this one common scheme of shortcut learning. So both adversarial examples as well as texture bias are two forms of utilizing a shortcut or shortcut features available in the data. And to give a more high-level perspective of this shortcut learning, imagine that on the left, I'm basically plotting the space of all possible decision rules. So as a decision rule, I'm quantifying anything which is an input-output relationship. Let's say the input is the image and the output is the class label. Can be anything. And usually, if you just randomly pick some decision rule completely randomly, then you will have very low performance, both on the training set and on the test set. Okay, and each machine learning model usually has some hypothesis base. So each machine learning model is just basically a parameterized decision rule, and depending on how you choose the parameters, a subset of all possible decision rules can be reached. And if two machine learning models have different architectures, then they can represent basically two different parts of this decision rule space. All right. Now, an important subpart of all decision rules are what I call training solutions. So these are all decision rules which actually perform well on the training set. And that can be as simple as just memorizing the label on the training data. So that would be complete overfitting. So let's call this overfitting features. It uses some features which are available in the individual images of the training data, but they're not necessarily helpful on IID test data. So we might see very bad performance on IID test data, and of course also in any kind of out of distribution data. All right, now in the space of training solutions, there's one subset of solutions, which is the blue area here, which are basically all decision rules which have both a high training performance, but also high performance on the IID test set. And these are basically all the solutions. This is the solution space that we typically look at machine learning. And these solutions don't necessarily work well in out-of-distribution tests, so most of these solutions will fail, but they seem to solve basically the data set in some other means, with some shortcut features like adversarial patterns or texture cues or whatever else. And then within this space of test solutions here, there are basically small subparts, each of which correspond to solutions that work well in certain OOD tests. Again, this can be adversarial examples, that can be texture cues or shape cues like cue conflict images or whatever else, you name it. But we expect there to be kind of an intersection of all of these OOD tests and in this intersection are solutions that kind of work well in all of these OOD tests. And this is what we call the kind of intended solution. So that is the solution that ultimately we want to have, typically at least, from a task. So when IMAGENET came about, right, and was finally solved, we were all very excited. And at least some of us thought that, okay, finally we made a huge step towards human visual performance, because probably in order to solve the task, the network really has to learn a lot about the physical world in order to solve the task. At least that was maybe my naive assumption when we went to these breakthroughs. But now, after a few years, that it's still very extremely impressive, but we've also learned all the limitations, and that we are still pretty far away from human vision, as exemplified also by adversarial examples. Okay, so this is the intended solution. That's kind of what we are hoping to get ultimately out of many tasks. So kind of solving a whole range of complex cognitive tasks, we kind of hope that ultimately we end up with something, let's say, like human vision, at least as an intermediate step, so to speak, because at least the human visual system is still kind of the gold standard that we're trying to match. All right, but we're not there yet. So usually, let's say on the Q conflict test, we usually have, our current solutions might use the texture bias, and then we have to change the inductive bias, for example, by changing the data in order to move into the region where we kind of pass this Q conflict test, so where we see a stronger shape bias. Or, we might be looking at adversarial examples, and, we might try to go from our undefended models, which are very susceptible, towards models which are more robust to local perturbations. But really, we should be aware that defenses, like adversarial defenses, are really just one way to push machines towards the intended solutions. It's by far not the only one. Right? And there are many more of these gaps, which are all probably due to some kind of shortcuts being utilized by the networks that we wanna fix simultaneously in order to move more closer and closer to the intended solution. All right, and this is here basically this much larger range of failure cases. And again, adversarial examples are really just one of the failure cases. And solving all of these failure cases here will mean that we have to change, let's say, the inductive bias, the model architecture, the learning architecture, and so forth. So all of these cases here are not isolated. So if we really succeed in solving one, we probably have solved a whole range of other problems and failure cases too. All right, now the question is, how can we push machines towards the intended solution, right? Well, there are generally four factors that kind of determine what representations the network will learn. One is, of course, the data. As I said before, in the data, there might be many shortcut cues that we as humans might not even be aware of. And this is particularly true for adversarial examples. So one way to go about this, for example, in the texture case, was to remove some of the undesired features in order to help neural networks avoid them. Now, this can work, for example, for texturization. It's maybe a bit harder for let's say, adversarial examples. Another point might be changing the objective. So as long as we're training only on a single task, on a single objective, let's say classification, then there will always be much more room for utilizing whatever shortcut is present in the data, compared to, let's say, a network that tries to solve a whole range of tasks simultaneously. And that's kind of what we as humans are doing. We are not solving just object recognition. We are basically ultimately we are trying to solve survival, obviously, but that kind of has a whole range of subparts. And one of the important things is that we very quickly understand our environment, how it will proceed in time, in the foreseeable future, in the next few seconds at least, right? And that we understand the geometry, and that we can very quickly generalize to new situations, right? If we first see a tiger, then even if we just have heard about a tiger and the description of the tiger, we should very quickly realize that we are in a dangerous situation and how we can get out of it. And this kind of awareness and very data efficient kind of one-shot generalization is extremely important for the survival of humans. And so clearly this objective and the task that we're trying to solve directly impacts what features the machine might actually learn. And the better we constrain this to more natural tasks, the more we can hope that some of the easy shortcuts, let's say like adversarial examples, can actually be avoided. Then we have architecture, of course, right? Convolutions are a very nice example of the right inductive bias, where we basically say, well, you know, natural images, the statistics of natural images are translation equivariant, so you know, we should be so using convolutions sets kind of the right inductive bias here. But of course, convolutions on the other side might also put in a wrong inductive bias, as we've seen for texture, right? So our convolutional architectures right now basically have a lot of processing power for local features, because a lot of the first layers have receptive fields which are very small and local. And there's comparative, like if you compare it, there's relatively little computing power for global computations in typical architectures like ResNet 50, which at least in part might explain why convolutional neural networks basically hook up on local features first and basically just sum them up, because it's more naturally suited to their architecture. So changing the architecture might already help in order to changing, for example, the shape bias of the network. And more generally, the architecture basically determines the inductive bias. And then, of course, there's the learning. Learning algorithms are also extremely important for the types of representations that we learn. So, for example, we know that large learning rates typically increase the preference for very simple and basically features which are shared across images, while using very small learning rates allows you to learn more complex patterns, but which are usually more specialized to a small set or even a single image. So these are basically all the knobs that we can tune. And you know, coming from that perspective, if you now look at a small range of defenses that have been proposed in literature, you immediately start to recognize that some of them, you know, basically turn some of these knobs in the right directions. So there's some potential that they can help, and some others, you know, don't really seem to turn any knob, and then any of these knobs, and so it's rather unlikely that this changes the situation. So in a recent paper with Florian and Nicolas, we looked at a range of defenses, you know, and whether they work, and one of them was actually the k-winners take all defense. And in this defense, you know, this defense is very simple. It just replaces ReLU activations with a k-winner take all nonlinearity. And of course, you know, that breaks gradient-based defenses, but if you think about it, it doesn't really change anything about the inductive bias or the objective or anything. So it doesn't seem to change really the features that the network would or could pick up from the data for this given task, right? And so that makes you suspicious for why this method should actually work if that's not the case, right? And indeed, the k-winner take all defense can be broken. Here's another one, which basically replaces the cross entropy with a different classification loss based on, you know, centroids, for which you kind of learn the centers. But again, you know, nothing really has changed about the problem. You didn't change the data. I mean, you changed the objective. It's really just a reformulation of the same classification objective. So there's no reason why suddenly the network should pick up different features. There's no change in the architecture, and there's no real change in learning in that sense. And so again, you know, from the outset, there is very little reason to believe that this would suddenly solve adversarial robustness, and indeed it does not. But there are also, of course, positive examples. So adversarial training being the most obvious one, because there the objective is really changed such that we basically induce this bias towards features which are stable, at least in a local environment. And the same is true also for Lipschitz regularization, where you basically put in a constraint, a smoothness constraint into the architecture itself, so you have some guarantees that the network cannot change more quickly than, you know, a certain speed. Also, the decision can only change slowly, basically. And if you combine this with a maximum margin objective, then you have a combination for which you can very well argue that this basically maximizes the smoothness of the architecture in a local region, and indeed that's basically what is happening, and it works against adversarials. Examples, but of course, unfortunately, not directly to other OOD tests. All right, so the main takeaway message, in a sense, that I want to give is that we shouldn't see adversarial examples as being an isolated failure case, but rather as something that is deeply connected to a whole range of other failure cases. And this is not even only in machine vision, but these failure cases arise in many other areas of machine vision. In privacy, you have that in natural language processing and so on. And in our perspective paper, we go into more detail there. So it's really a very deep problem that we're trying to solve, and not just this isolated case. And if you think about solving this problem, we should think about basically the evolution, or I would argue that we should think more about the evolutionary pressures under which the human visual system developed. Because obviously humans have developed this robust visual system for a reason, not just by accident, right? We developed a shape bias for a reason, and not because if you only basically would have to solve object classification, then it would have been completely sufficient to use some texture cues. But that's not really the task that we're trying to, or that we try to solve, or that we have to solve in order to survive. And so basically we should tune these knobs and align them a bit more with what we know from human learning and human evolution, right? And there are a few, I obviously cannot give you an answer right now what we have to do, or what the right turning of these knobs actually is. But it's clear that if you go into data, it might be at least valuable to allow such kind of active interventions in the environment from which humans can quickly learn the physics of the world in a fairly unsupervised way. So if you think about ImageNet, it's actually such an artificial task, right? We basically this is just blobs of pixels, right, from which the network has to select somehow some features in order to classify the images, but there's very little to no information really about the physical nature of objects, that they are like 3D objects which can turn, which can rotate, which can scale, and so on. Nothing of this is really, or is only indirectly encoded in the data set. And so that's why neural networks have a hard time learning any of this, and in particular also shape, right? Because that's a physical property which is not super obvious if you have never seen a natural environment or our physical world beforehand, right? And that's why it's pretty natural that networks are using these kind of other shortcut features that we don't tend to use, simply because they are available and they're easy to learn, they're nicely correlated. Whereas shape is something very complex, very nonlinear, it changes, with viewpoints and so on. And so it's a much harder thing to learn, in particular so if the only thing that you know is ImageNet. Then of course there is the objective itself, right? We are not only doing object recognition. Again, for that it would be completely sufficient to take texture, but we have all these other tasks that we need to solve in order to survive. And then of course there are the architecture and learning. And that's kind of the hardest one, because we don't really understand how our evolutionary pressures and our inductive biases are embedded in the architecture and the learning process itself. It's just clear that this happened. So somehow, it's amazing how quickly little children develop a very general understanding of our physical world. And so it's fairly likely that many of the inductive biases about our world are already embedded at this stage in the physical connectivity of the brain or in the learning mechanism. And I don't think we even understand really completely what the inductive biases are of the architectures that we're using today. But I think this will be a very crucial. Furthering our understanding in this area will be very crucial in order to make progress in these areas. All right, now as a last highlight before coming to conclusion, This is very recent work where we try to transfer a little bit of knowledge from neuroscience to machine vision systems, and we looked at whether or not this actually helps robustness. So what we did here was very simple. We basically we showed images both to a machine vision system and to real neurons, so the visual system from monkeys. And we basically wanted that that our neural network tries to replicate, or is at least able to predict, the neural responses that we measured in vivo. And the reasoning behind that was that by doing this, we hope we could basically regularize the neural network responses such that it is or has to pick up features which are more aligned with what a monkey visual system would actually pick up. And I'm not arguing that we succeeded in that sense, but at least we see a small effect. So you see increased robustness compared to baseline performance, or also a shuffled version of the tasks. And I mean, the increase is not huge, so I'm not arguing that we should all use this as our defended baseline, but it was definitely interesting to see that there was, that we could see an effect. And this could also be a direction, basically trying to transform more from neuroscience is definitely a direction that could also prove fruitful in the future, at least if you understand also the neuroscience side a bit better. All right, so with that, again, thanks for listening. I try to argue as adversarial examples as being kind of the clearest gap between human and machine vision, and taking adversarials or adversarial robustness as kind of a benchmark, or as one benchmark to measure progress to close this gap. And I believe that adversarial perturbations are really connected to a much larger set of failure cases through what I called shortcut learning. So that neural networks seem to be using features in the data sets and the tasks that we are not sensitive to, but which can explain why they behave so differently in out-of-distribution tests. And eliminating this shortcut learning definitely has the potential to overcome many generalization issues in machine learning. And so by solving adversarial robustness, there is at least some hope that we can solve a much wider range of failure cases. And one way to go about this might actually be to basically match the evolutionary pressures under which the human visual system developed its robust feature selection. And with that, again, thank you for listening. This is the group that supported and has done all of this work. And of course, I'm also thankful to my collaborators, in particular, of course, Matthias Bethke, who has been extremely supportive, but also Andreas Tolias, Felix Wiechmann, Bernhard Schölkopf, and Oliver Brinkmann. All right, thanks a lot.
Okay, so thanks, Wieland, for the nice talk. We got a bunch of questions in both in the Q&A and in the general chat. So I'm not sure you can read them, or if you want, I can read them for you. Then you can answer.
Yeah. No, I think I can read them. So maybe should we just go through the Q&A, and I think in the chat it's mostly the same questions as far as I see. And
yeah, some of them are repeated.
On the Q&A.
You can start with the Q&A, and then I'll just check if there are some others in the chat that are different.
Yeah. All right. So the first question is about model interpretability tools like CAM, which I definitely believe are important. I mean, the BAGNET in a sense is similar, that it shows you which parts of the image are important. I guess the question is, first of all, how reliable are the interpretability tools? For one, the second one is they might be able to detect some shortcuts, but probably, they might also be deceptive or keep us in thinking we now understand what's going on. So I think there's kind of a dual mode here. But definitely understanding, I think more generally, understanding what features are being used by the methods, which is kind of the ultimate goal of all interpretability methods, is very much worthwhile to to exactly study whether the networks are doing what we hope they do. The next question is about neurosymbolic models, which I'm not sure I understand enough about to comment this question. So I don't think I can say anything intelligent on that.
Yeah, maybe we can. Yeah, you can continue then if the Abigail can specify what I mean. This was the meaning of this sentence a bit better. Then maybe you can try to address.
That would be super cool. Yeah. The next question is about controlling like how shortcut learning is related to now things jump here to shortest path movements in control theory. I mean, yeah, I mean, and whether you know maybe similar techniques can be used to avoid shortcut learning. I mean, I guess in the example of the shortest path, it's a kind of very clear and classical control problem where we know what we're doing and optimizing. In a way, the problem of shortcut learning is that we usually don't even know how to measure it or understand it. And so there's, I think, as soon as we can, you know, have a quantifiable measure of, let's say, you know, shortcut learning, then of course we would also have a handle on maybe eliminating it with optimization-based techniques. But I think right now this is pretty much out of reach at the moment. The next is about the example domain. Indeed, I'm coming from machine vision. So as you all noticed, basically all of my examples have been in the image domain, which is of course also the area where most, where adversarial examples are most studied. But indeed, I believe that most of the, you know, of what I said generally about shortcut learning is present in all other domains too. So in NLP, actually, this is well known. In the last 2 or 3 years, there have been several results on, you know, basically how or what features are being used by, you know, question answering models, for example. And they often, you know, can pick up shortcuts that we have not been aware of, like certain, keywords is kind of maybe the easiest one. Certain structures in the sentences that kind of give away the answers. But once you understand what the shortcut is that then neural networks are using, it's also very easy to construct examples which trip neural networks but not humans. So yeah, I think the type of problem is pretty similar. Should we move all cameras towards binary vision? Let's say it like this. I mean, cameras. What I argued, or what I started to argue also in the talk, is that probably these, you know, just training on ImageNet will be pretty tough. Like in order basically to get human vision on ImageNet alone will be tough. And that's for the simple reason that there's very little physics involved, or there are few ways for the models to really understand physical properties. Meaning that there seem to be a whole lot of shortcut features which are much easier to learn than something like human vision, which has basically, first of all, of course, the 3D vision, which makes it much easier to understand our 3D world and to learn basically a general set of transformations under which objects usually transform, which makes it much easier to generalize once you understand that concept. But understanding that concept really is probably, I mean, first of all, temporal vision, or like where you basically see objects moving and rotating, and you always know without actually having any labels that that the different viewpoints of an object, for example, are related. That's definitely a very important cue for in the development of human vision to understand object structures. But of course, this is also supported by binary vision. Now, this can definitely be an important stepping stone, I think, or an important way of making it easier for models, or to increase the inductive bias towards more physical properties of our world. The hardware gap, that if we had much more resources. Oh, that's a tough question. So basically the question is, you know, whether you just throw on more hardware, basically more neurons, like let's say GPT-2, you just basically scale things up by a factor of 10 or a factor of 100, whether we will then move to more human vision level. I guess the answer it will be in part yes, in part no, maybe. So in a sense, I mean, if you look at the at this Facebook model, which was trained on 3.5 billion images unsupervisedly, I think they succeeded in avoiding a few of the trivial shortcuts that are still okay on ImageNet scale. So I mean, this model is kind of state of the art in a range of kind of OOD generalization data sets like ImageNet C, ImageNet A, and so on. And I guess that's for this particular reason, because it picks up more natural and more interesting features from the data set, because it had to scale to such a diverse and large data set. So it definitely gets you some way. What I'm not sure about is whether, but basically just scaling up things will not remove all shortcuts. So for example, if you think about the context biases that you have, I showed this example with a cow on the beach, right? Even in a very large data set, let's say 3.5 billion images, you will still have this context bias. You will still have most cows on a greenish grassland and very few cows on a beach. So these kinds of shortcut features will still persist and are useful in order to solve the task. So I think there will be a certain limit on scaling, but where that limit is, I don't know. The next question is, avoiding shortcuts sounds roughly equivalent to avoiding poor local minima. Would there be some form of regularization that would help other than Lipschitz smoothness? So I'm not even sure whether shortcuts are equivalent to poor local minima, in the sense that for a given task, they're not necessarily, like our intended solution doesn't necessarily work better than the shortcut solutions. So in that sense, I wouldn't argue that shortcuts are poor local minima. They're only poor from the perspective of our generalization tests. But of course, the neural network didn't know nothing about the generalization tests that we want to perform at the end. But of course, if you can try to quantify what you think is a poor local minima by additional regularization techniques. And yeah, adversarial training or Lipschitz smoothness is definitely probably among our best ways right now in the context of adversarial examples. I mean, other regularization techniques can be also self-supervised techniques where you try to train the model to pick up certain more relevant features for those tasks, or also just generally introducing additional subtasks, let's say surface normal estimation, which tries to bias the feature selection of the model more towards physically relevant features. So there are definitely ways, I guess, to get around some of the local minima that we don't want, so around the shortcut solutions that we don't want. But it's an open question what the right regularization techniques actually are.
Okay, I think we don't have any more questions in the Q&A, but I just got some follow-ups in the chat. So there's one from Rafael Labaca Castro, and he says, thanks for the great talk. Regarding the evolutionary pressure on humans, what if humans developed this for survival because they weren't really confronted against natural adversarial cases, as much as we in some domains are or could be?
That's a very interesting question, yeah. And it kind of relates to a whole debate as to whether humans are truly adversarial robust or not. So whether basically one can perform or would be able to perform adversarial attacks on humans similar to neural networks. Now, I think that's an open question, and there's very little factual evidence that one can provide in this argument, which is why it's not settled. But I would personally be extremely surprised if humans would be susceptible to such minimum norm adversarials. I mean, there are certainly, at least in the sense of neural networks, right? I mean, we know, of course, there are kind of things like illusions and stuff, but they typically work only on very specific images in very specific settings. But the problem with neural networks really is not only that they can be fooled by small perturbations, but that you can basically generate perturbations which can flip the decision of the network to any other class, right? It's not just one class close by, but it's really, you can basically make absurd transitions in a sense. And I have a hard time believing that this exists for humans. At least I would have expected through the last few thousand years for some people to come up with such interesting illusions that can, flip a more or less random image into more or less a random class. But that's a belief, it's not factual evidence. So we have to see.
Yeah, then there is a follow-up by Abigail about these neurosymbolic models. So there is a link to a paper, and then there is some clarification of what these neurosymbolic models are. And it is that the composite system, known as a neurosymbolic model, leverages both a neural network to recognize the colors, shapes, and materials of the objects, and the symbolic system to understand the physics of their movements and the causal relationships between them. So the question is actually if these models help, may help with these issues of identifying out of distribution samples.
Good question. I think it has to be seen. Right. I mean, there is a lot of, sure. I mean, there is, I guess, some hope that introducing maybe some more symbolic representations can help. But as we all know, the devil is usually in the details. So I think we have to see. Nobody knows, I guess, at this point in time. But I would be happy if that gives some, I mean, let's say like this. On the positive note is that what I do believe is that there is no easy fix for the problem, for the reasons that I try to argue in this talk. We are not going to solve adversarial robustness or any of the other gaps by just changing a single little knob, like a small silver bullet in the architectures, and then suddenly and magically things will work. I don't think this is happening. So basically going a bit crazy and trying to kind of getting symbolic logic into the game, maybe that's a game changer. I don't know. I cannot judge, but I definitely appreciate tries to, trying to break out and try new crazy stuff. So that's all I can say, I guess, at this point.
Mm-hmm. Yeah.
There's a, maybe
another
I'm not
one.
sure, but is there another question before that? So there's a question in Q&A about spike neural networks.
Yeah.
Yeah, I mean, I personally worked a lot on spiking neural networks, so generally, and we actually, a few years back, I was actually working in a little bit on this question, basically, whether this would help. But again, I think it's mostly about, I mean, the question we always have to ask again is, would a spiking neural network per se change the features selected by the neural network to solve the task? And my general prior would be no. I don't think it would, like, why would it suddenly change the features it selected? At least that would be kind of almost arbitrary. It's not really, whether you're spiking or have floating responses, I'm not sure that makes a fundamental difference. So I wouldn't think that this alone would, or I wouldn't know why this would solve the problem, let's say.
Yeah. So we are perfectly on time. I think we still have 5 minutes for live Q&A. So I don't know if we have any other questions from the other panelists or chairs. And another thing is that there will be a break after in 5 minutes. So Wieland, in case some of the attendees would like to talk to you, if you could provide like a Zoom room, we can share the link, and then if some people want to talk to you in the next 30 minutes during the break, then maybe if you're available, they can join this room, and then you can keep going with some discussions. And This will be not recorded, so we don't have any privacy issues, so people can show up and talk.
Yes, I'll check out the link and